So this evening I want to talk about the past, present and future of cancer therapy and to try to answer a few key questions. How old is cancer? Why is it so difficult to treat? Why do deaths from cancer sadly seem to be increasing? And how did a medieval religious miracle transform 21st century cancer therapy? First, though, I should probably explain what on earth an engineer is doing talking about cancer in the first place. So although my first degree is indeed in mechanical engineering, for the last 20 years I've been working on methods to try to develop, better methods for delivering cancer chemotherapy. So many of you will probably have seen this headline from 2015. This is from a Cancer Research UK report. 1 in 2 people in the UK will sadly be diagnosed with cancer at some point in their lifetime. And if we look at the worldwide picture, it's not really much better. Cancer deaths have been increasing over the last 30 years. Before we get too depressed by these figures, though, there's one vital piece of information missing from these graphs, and that's the corresponding change in life expectancy. Thanks to public health measures such as vaccination, improvements in sanitation, life expectancy has improved dramatically over the last century. In 1940, the global average life expectancy was 43. By 2019, it was 73. And if we take that change into account and we look at the cancer figures, actually the death rate has been dropping by 20% in the last 30 years. It's just unfortunately the price of longevity is that we're more likely to die from cancer than from other diseases first. And it does remain an incredibly difficult disease to treat. To explain why, I need to say a little bit about what cancer actually is. So something, and I will come back to what that something is later, goes wrong with the DNA in our cells, and it causes them to replicate out of control. In healthy tissue, normal cells divide at a very, very controlled, regulated rate. Divide. If something goes wrong, if a cell becomes injured or infected, then a pre-programmed pre-programmed death kicks in, a process known as apoptosis. That cell self-destructs. And then specialist immune cells known as phagocytes come in and remove the debris. So the corrupted DNA doesn't get passed on to the next generation. Unfortunately, what happens in cancer is that process is switched off. The corrupted cells can replicate out of control. They actually replicate faster than in normal tissue, with the result that we end up with this rapidly growing mass or tumor, which eventually chokes the healthy tissue around it, causing it to shut down. And the other problem is because of the way the cancer develops, it makes it incredibly difficult to treat. So if we look at the structure of the tumor, we have this very rapidly proliferating tissue. What that means is that as the tumor is growing, it starts to actually recruit its own blood vessels from the surrounding tissue. But because it's growing so fast, the structure of those blood vessels is really chaotic. So some parts of the tumors get lots of blood, some get absolutely none. The fast-growing tissue also squeezes the vessels that are draining the tumor, so we end up with a very, very high pressure in the tissue, makes it almost impossible to get enough drug in to kill the damaged cells. Even worse than that, because of this chaotic blood supply, many regions of the tumor don't get enough oxygen, and when you deprive cells of oxygen, you change the way that they behave. Their metabolism changes, even their DNA starts to change, makes them very, very difficult to kill. And it also sadly kicks off another process known as metastasis, where these cells break away from the tumor, they spread to other parts of the body and start new tumors. And sadly, it's those metastatic tumors that tend to be fatal. At the same time, the cancer cells also start to secrete chemicals, or they express molecules on their surface that switch off the immune response. They become invisible to the immune system, and they also start to evolve faster than the healthy cells around them, which means that they become resistant to treatment faster than the healthy tissue. So apologies, this diagram is a little bit complicated, but what I wanted to illustrate is why this has been such a formidable challenge for medicine for so many centuries. Now that brings us on to the next question, which is, how old is cancer? If you stumble into certain parts of the internet, you would be forgiven for thinking that cancer is a punishment for our godless modern ways. It is most certainly not a modern disease. There is archaeological evidence of breast cancer, of prostate cancer, and bone tumors from across the world in mummified remains from South America, from Siberia, and also from ancient Egypt. And actually in 2016, a reanalysis of a toe bone taken from a human skeleton from 1.7 million years ago was found to be evidence of a bone cancer. And then actually, in 2020, in the Lancet Oncology, a paper was published, the first evidence of cancer being found in a dinosaur bone from 76 million years. So 5G is not responsible for cancer. It also doesn't seem to have been a particularly rare disease. This was a study published last year from a group in the University of Cambridge where they analysed skeletons from a lot of medieval cemeteries, and they discovered there was evidence of cancer in about 9 to 14%. It may not have been what killed these people, but it was certainly present. And it was certainly common enough to have been referenced in a lot of ancient medical texts. So this is a fragment of an ancient Egyptian papyrus, the so-called Edwin Smith papyrus, which is the collector who purchased it. This is an amazing document. It's a handbook for surgeons. It describes lots of really, really interesting treatments. It's the first documented evidence of the use of salicylic acid from willow bark, which we better know as aspirin. And it even describes methods for treating tumours by surgery. It describes something which translates as a fire drill. We believe what that is a device such as this for starting a fire, whereby the friction at the tip of the stake leaves you with a very hot point, and that enables you to remove the tissue very, very quickly and also cauterize the wound. One case, though, case 45, is rather more sinister. It describes a tumour that's spread across the breast and feels very cool to the touch, and that's thought to be a description of late-stage breast cancer. Sadly, in this case, the treatment advice is extremely brief. There is nothing, and that's a verdict that hasn't changed really since that time. Now, moving from 3000 BC through a little bit closer to modern times, and the most famous physician, perhaps of all, is Hippocrates, and he's at least credited with coming up with the term cancer, possibly because he likened the appearance of a tumour with its feeding vessels to that of a crab. I think you possibly need an astronomer's eye to see that. But Hippocrates' advice on medicine dominated both Western and indeed Arabic thought for really 1,500 years afterwards. And that included his explanation for the origin of cancer, which, like all other diseases, was thought to be due to an imbalance in the four humours: blood, phlegm, yellow bile, and black bile. And cancer in particular was thought to be due to an excess of black bile. Now, there were many treatments put forward to deal with these humoral imbalances. Celsus and Galen were two of Hippocrates' followers a little bit later in the 1st century. And they came up with many, many complex treatments, many magical spells, potions, and indeed certain types of surgery and bleeding to try and drain the humours and restore balance. Hippocrates himself, though, actually had very, very sage advice for the treatment of cancer. That was leave it alone. Presumably, empirically, it was noticed that many types of cancer, actually, if you attempt surgery, you simply accelerate their growth and, sadly, the death of the patient. Now, this advice probably saved a lot of patients' lives. Ancient surgery was a pretty harrowing experience. This was long before anaesthetic, antiseptic, or antibiotics. But this did sadly mean that patients throughout Greek, Roman, and into medieval times were left with relatively few options. The power of prayer, magic, or whatever the apothecaries could offer. To be fair, some of their remedies were very, very effective. Opium, for example, remains a mainstay of pain relief for cancer patients nowadays, and indeed some of the herbs that were used in medieval times became the basis for modern cancer drugs. There were, however, a few remedies which you possibly more expect to find at Hogwarts or in Macbeth: dragon's blood, white vitriol, I believe fox lungs, tortoise liver, and perhaps most weird of all, crab's eyes. We don't know whether that was the idea of fighting like with like, but this was what a medieval cancer patient sadly was expected to manage. And it wasn't until really the Renaissance, 16th century, that people started to question whether this was really a realistic explanation of cancer, and in fact whether black bile existed. So scientists and anatomists such as Andreas Vesalius started to do investigations on the human body and was quickly realized that black bile didn't exist. That was very good news for science. Whether it was good news for patients is arguable, because what it did encourage was many more experiments into surgery. Now, I've tried to keep the number of gory pictures in this lecture to a minimum. This was one of the least harrowing ones that I could find, but I think it does illustrate very much just how terrifying surgery was throughout, most of modern history. And bear in mind, antibiotics were a very, very long way away in the 20th century, and the best anesthetics at the time were either opium or alcohol. That aside, by 1800, a Dictionary of Practical Surgery was recommending surgery as the only way for treating cancer. So Hippocrates' advice had almost been completely reversed. We don't know how effective it was. Records were not kept. But if I tell you that most surgery took place in an open theatre like this, in a pit with medical students looking over, absolutely, certainly no masks. Surgeons would be operating in frock coats and would frequently move from patient to patient, barely washing their hands, certainly not changing their clothes. We do have to wonder just how many patients did survive. Fortunately, a little bit later in the 19th century, two inventions or two developments changed that dramatically. The first was the invention, or at least the implementation, of effective general anaesthesia. So this is a reconstruction of a demonstration by William Morton, which is the first use of ether in a surgical procedure to make the patient unconscious so that they could tolerate the procedure without too much pain. And this very, very quickly took off surgery across the world. Similarly, pioneers such as Louis Pasteur and Joseph Lister, with the discovery of bacteria and the origin of an infection, worked out ways by which this could be minimized in surgery. So this engraving is showing carbolic acid being sprayed onto a patient during surgery. And in fact, one of Joseph Lister's first operations was for breast cancer on his own sister. You will note, however, certainly no gloves, no masks. Surgeons are still wearing frock coats. And it took a little while for anesthesia and antisepsis to become widespread. There's one more figure I need to recognize, and that was William Halsted. He was a very formidable figure at Johns Hopkins, Baltimore. He was a lifelong opium addict, an insomniac, and he put his medical students through possibly the most rigorous training program ever known. And he had a rather fundamentalist view, shall we say, of surgery, removing huge amounts of tissue to treat cancer and often leaving patients with even more debilitating conditions than they'd started with. We do credit him, though, with developing the very rigorous procedures now that surgeons go through. Before operating, scrubbing, wearing gowns, he even instituted his own range of rubber boots and rubber gloves. So we're quite relieved some of his teachings on how to treat breast cancer, for example, are no longer with us, but he is also responsible for the fact that modern surgery today is probably the most effective treatment for cancer. Certainly in the UK, nearly half of patients still receive that, and in many cases it is curative. Now, around the same time as these developments in surgery, there were two other huge developments. The first was the use of the experimentation on vacuum tubes, and particularly the discovery by Wilhelm Röntgen of X-rays. So this is the very famous picture of his wife's hand, taken with these magical rays emerging from a vacuum tube. And amazingly quickly, this discovery got taken up as a potential cancer therapy. So the discovery was in 1896. By 1901, radiation X-rays were being heralded as an absolute cure for all forms of cancer. I probably don't need to say that that claim sadly wasn't realized, but extremely quickly, people started to apply this as a cancer therapy. Now, the reasoning behind it came from an observation of factory workers making vacuum tubes, that their hands and nails started to flake and redden and become swollen very, very quickly. And it was hypothesized that the reason for that was that our nails grow much more quickly than other types of tissue, and that was why they were more susceptible to the radiation. And therefore, could this be applied to the rapidly growing tissue that we find in tumours? And even a year after Röntgen's publication, radiotherapy clinics were popping up all over the world. Devices such as this. So the lady here is holding up a lead mask to shield her face from the X-rays with a hole in it where, in this case, it was, I believe, a jaw cancer that was being treated. And some treatments even involved implanting radioactive material into a tumour to try to kill the cells. This was 50 years before anyone had discovered DNA, but actually they were spot on as to how the radiation was working. What actually happens, we now know, is that radiation damages DNA either directly or by causing the chemical breakdown of water, which in turn produces reactive oxygen species that also kill the DNA. And so once the DNA is damaged, the cells can no longer replicate. This was why fingernails were flaky, and it was also why it was able to slow the development of tumours. Sadly, however, there were some serious side effects. This is an example of the side effects that you can get from radiotherapy, and it was very quickly noticed that patients were suffering from these. It was no use against cancer that already spread, unfortunately, and possibly the most serious problem was radiation resistance. So as I mentioned a little bit earlier, cancer cells evolve really, really quickly, and so repeated treatments become less and less effective as the radiation stops having an effect. Now, to try and overcome that, we've come a long way in our radiotherapy machines. Modern radiotherapy systems use very, very high energy, very short bursts of radiation from multiple beams to try to maximize the amount of radiation ending up on the tumour and try to minimize the amount of healthy tissues that's being exposed. Radiation resistance, though, and side effects still are a big problem. And so just over a quarter of cancer patients now receive radiotherapy, but it's usually in combination with some other treatment. A totally different approach was being taken in Germany. So Paul Ehrlich, who probably deserves a lecture in his own right, was looking at microbiology. He was looking at dyes that could be used with microscopy to study bacteria. And he noticed that some types of dye were very specific to certain types of cell. And so he postulated that it might be possible to develop a drug that would only act on cancer cells. It would leave healthy tissue unaffected. And he called this his magic bullet. And this idea captivated scientists, clinicians, even royalty in Germany, to the extent it was actually immortalized in a film in the 1940s. And this concept of the magic bullet has remained as the holy grail for cancer therapy ever since. Now, sadly, Paul Ehrlich died before he could realize anything, and the idea, the magic bullet, just never really developed. The first candidate, though, came from a very unlikely source. In the aftermath of the First World War, physicians treating soldiers who had sadly been exposed to mustard gas noticed that there was an unexpected effect on the bone marrow cells. Those cells seem to be disproportionately affected by the mustard gas compared to healthy other cells in the body. It took, however, another 20 years and the aftermath of the Second World War for anyone to realize that might be applicable to cancer therapy. And the idea was that it might work in the same way. Bone marrow cells also replicate very, very quickly, and so perhaps this drug could act on the rapidly proliferating cancer cells and stop them from growing. Now, it doesn't work in the same way as radiation. It actually works by a chemical process known as alkylation, but the drug binds to the DNA in the cells, stops them from being able to replicate. And so this became the basis for the first chemotherapy drug. Around the same time, a group in America led by Sidney Farber at Harvard Medical School was working on a different approach. So they were trying to block the action of certain nutrients, in this case folic acid, on cancer cells. The idea being that if you can stop the nutrient from getting to the cell, it can't grow. So they discovered something called an antifolate drug that would stop the folic acid being taken up and hence prevent the cell from dividing and replicating. Now, unfortunately, neither of these drugs, the mustard gas derivative or the antifolate, were actually that effective. Initial results looked very, very promising, particularly in childhood leukemia, but the cancer in many cases came back very quickly. What Sidney Farber, though, did do was massively raise the profile of cancer, particularly in the United States. He recruited Hollywood stars from baseball and American football, and even very, very powerful New York socialites to his cause to lobby Congress to launch the war on cancer. And what that led to was the founding of several institutes, and particularly the National Institute for Cancer Drug Discovery in the States. And very quickly, these two types of drugs were joined by a whole battery of other chemotherapy agents. Some of them derived from natural sources, such as periwinkle and the yew tree. Others from minerals, such as platinum. And interestingly, in some cases, they were drugs that had been developed for other purposes. So, for example, antibiotics. They were found to be very effective against cancer. And even some dyes, going back to Paul Ehrlich. And once these drugs had been created and started being used in combination, their efficacy on cancer improved dramatically. And so again, this is now a frontline treatment. Many, many cancer patients, nearly a third, receive combinations of chemotherapy drugs in modern treatment. So this led to the three pillars of cancer therapy, still certainly in the 20th century and still largely today: surgery, radiotherapy, and chemotherapy. There are, however, a few other treatments that I think deserve mention. When we talk about radiotherapy, we nearly always mean X-rays or gamma rays, so very, very high energy radiation directly damages tissue. Other types of radiation, though, can be extremely useful. So, for example, visible light and microwaves, they don't carry enough energy to directly damage the DNA in cancer cells, but you can deposit enough energy in the tissue to destroy it. So this is an example of a liver tumour that's been treated with microwaves, and as you can probably see, basically it's been cooked. So microwave ablation and laser ablation are now for certain types of tumours, are two very, very effective treatments. And the third one is the rather unfortunately named radiofrequency ablation. I need to state now, this has nothing to do with radio waves, so you are completely safe to turn on the news tomorrow morning. It's actually a very rapidly oscillating electric field, but it works in a similar way, deposits enough energy in the tissue to break it down and destroy all of the tumours. The disadvantage of all these techniques, though, is a probe needs to be inserted into the tissue for it to work, and sadly that means you can't use it in all areas of the body. Another treatment that overcomes that is very, very high-intensity sound. So sound waves can penetrate pretty much anywhere in the body without needing to insert a probe. And they, similarly, if they are of sufficient intensity, they can also heat the tissue up enough to destroy it. Now, the disadvantage of this approach is it's very, very slow. You basically have to paint the tumour out piece by piece, so it can take several hours to treat a tumour. But it is looking very promising, and actually in the last 7 years, there have been two very exciting trials on applying this for the treatment of brain tumours, which are extremely difficult to treat. It's very difficult to do surgery on them. And so hopefully in the future, this is going to become another weapon that we have against cancer. Now, I mentioned side effects. Both radiotherapy and chemotherapy, one of the major disadvantages is they produce absolutely horrific side effects. So there have been many efforts to try to reduce those. One is to encapsulate the drugs in tiny particles, nanoparticles, to try to get them to locate preferentially in the tumour. So instead of just injecting the drug into the bloodstream, it's first wrapped into a little particle, usually of some sort of polymer. And that particle is created of a size that will leave the bloodstream in the tumour. So I mentioned earlier that one of the characteristics of a tumour is you have this really chaotic structure. Another thing is those vessels are slightly leaky. The cells in them are further apart than in healthy tissue. And so if you have particles of the right size, they can escape into the tumour, whereas they can't escape into healthy tissue. And so the idea is that by doing this, we can try to maximise the amount of drug that ends up in the tumour and avoid it ending up anywhere else. Now, so far, this hasn't proved to be enormously efficient. It's probably only improving things by a few percent, but that can in some cases make the difference between a patient receiving enough drug without the side effects versus not being able to receive the treatment at all. Now, possibly a more efficient treatment is so-called photodynamic therapy. So this uses a type of drug that is completely inactive until it's exposed to light. So the drug can be injected safely into the body. It will have no effect until laser light is shone on the tumour to activate the drug locally, kill those cancer cells, but hopefully without having any side effects elsewhere in the body. And this has been used very, very effectively, particularly in the treatment of skin cancer, and it's being very, very extensively explored for a lot of other tumours at the moment. The challenge for it is that it's quite difficult to focus laser light very deep in the tissue. I'm loath to do the demonstration with the laser pointer, but light doesn't penetrate very far, only a few millimetres, so it's really only suitable for skin cancer or cancers where you can stick a probe. There is, however, research going on to see if there are other types of stimuli, for example, ultrasound, that might be used to excite these drugs as well. Of course, probably the most, the biggest contribution to biology of the 20th century was the discovery of DNA by Crick, Watson, Wilkins, and Franklin. Not only did that facilitate a genetic understanding of the origins of cancer, it also gave the possibility of another type of cure. So so-called gene therapy was conceived almost immediately after the discovery of DNA, the idea that we might be able to correct this corruption of the DNA damage that's causing the cancer and hopefully therefore reverse the tumour. Now, so far, efficacy has been pretty limited. There are several research studies that look very exciting. It's yet to become a mainstream treatment. But with some of the developments in gene editing, such as CRISPR-Cas9, this has become a very, very active area of research again. And the idea that we might be able to correct cancer at its origin is very, very exciting. There's one more area of therapy that I need to devote some time to, and that is immunotherapy. Now, for certainly 500 years, there have been many, many stories of cancer patients being miraculously cured, seemingly with no treatment. This is Saint Peregrine. He's the patron saint of cancer, and the reason that his bare knee is showing in this sculpture is that he was cured overnight of an ulcer, which was thought to be a cancer now, seemingly by the power of God, and it was the night before his leg was due to be amputated, so it was extremely timely. And for many, many years, people started to report this happening, and by the 19th century, started to be noticed that these miraculous cures seemed to coincide with patients having other types of infection. Now, sadly, this initially led to some deeply, deeply unethical clinical trials. I hesitate to even call them clinical trials. These included taking bandages from infected patients, transferring them to cancer patients, injecting breast cancer patients with gangrene, and uterine cancer patients with syphilis, the last on the pretty tenuous grounds that prostitutes never get cancer. This was the state of clinical trials. I think things are better now, thank goodness. There's no record of whether any of these was successful. Fortunately, a doctor in America, early 1900s, William Coley, put this on a more systematic basis. He was deeply intrigued and indeed deeply frustrated by an observation that he'd had a patient who had died despite seeming to survive the surgery extremely well. Another patient who suffered a horrible infection post-surgery had been cured of cancer. He became obsessed with this and eventually tracked down the reason to a particular type of bacteria that causes an infection called erysipelas. And he started to wonder, would it be possible to turn this into a therapy? And so he developed a series of bacterial broths. He would take meat broth, he would allow it to develop a bacterial growth, he'd then purify it and strain it, and that would be the drug that he was injecting into his patients. And in many cases, it was incredibly effective. But there were two problems. First of all, his scientific record keeping left a lot to be desired. He published his reports in the form of case reports rather than in the major scientific journals. And perhaps more importantly, he had absolutely no idea why it was working. And it didn't work in all patients. So sadly, at the time, he was competing with the much, much more intuitive and I have to say commercially lucrative chemotherapy and radiotherapy that were being developed. And those two became the mainstream treatments. Well, Coley's toxins, as they were known, became less and less accepted by the mainstream medical community, and eventually by the 1960s, they were actually included on a list of the American Cancer Institute known as, officially known as unproven cancer treatments, more commonly known as the quack list. And there they might have remained, but for a few very determined and very stubborn individuals. The first of whom was actually his daughter, Helen Coley-Nortz, who took on the mammoth task of trying to compile her father's notes, which were in a barn, try to develop some sort of systematic explanation for what might be happening. And actually, she may be credited with having worked out the connection between these toxins and the immune system. Similarly, clinicians such as Steve Rosenberg, who had a similar experience to William Coley, observing complete remissions in patients following bacterial infections. And they weren't prepared to accept that it was just by chance. And then huge credit has to go to the scientists who eventually worked out the mechanism by which these therapies were working. So James Allison and Takusa Honjo were rightly given the Nobel Prize for Medicine in 2018 for their work on immunotherapy and starting to understand why this was happening. So why was it happening? Well, I'll explain. The concept of immunotherapy is beautiful. It's incredibly simple and incredibly elegant. Our immune system has evolved to protect us from invaders. It is there to protect us from disease, to get rid of infection, and to protect us from future infection. So if we could turn the power of the immune system on cancer, that would be far better than any drug. The problem is the reality is incredibly complicated. This is a poster that we have up in our laboratory. It's showing a small subset of the pathways that are involved in immunotherapy or in cancer immunology. More than that, this gets updated every year. This is a very active field of research. We do not know everything yet. So with that caveat, and the further caveat that I am not an immunologist, I want to try and explain the basic principles by which immunotherapy works. So, key to our immune system is the chemical composition of cells. So when we have a foreign cell, for example, a bacterium, a virus, or a cell that's been infected by a virus, the chemical composition is very different from our own body cells. There are molecules on the surface known as antigens that are recognized by the immune system. The other key class of molecules are antibodies. So these are molecules either present on the surface of immune cells or released by immune cells. And the antibodies are designed, if you like, to act on a particular antigen. They're like a lock and a key. And if an antigen and an antibody come together and they link, then an immune cell will recognize that. The antibody will link to another molecule on the immune cell surface called a receptor, and the immune response will be triggered. And so T cells and other types of killer cells will come in. They will attack the foreign cell and remove it. In healthy tissue, our cells, the cells that are supposed to be there, they have no foreign antigens. So when they encounter an antibody, there is no binding, so there is no immune response. In cancer, things get a little bit more complicated. So cancer cells are diseased. They do express antigens that should be recognized by the immune system. Antibodies will bind to them, and so an immune response should be triggered. The problem is that cancer cells also express other molecules on their surface that switch off that response. So these are known as checkpoints. So these other molecules on the immune cells bind to cancer cell, and it stands down the immune response. And this is one of the many, many problems with treating cancer, is that not only is it difficult to get enough drug in there or to treat them with radiation, the immune cells that are present get switched off. So the purpose of immunotherapy is to try to switch that response back on. And there are lots of different ways of doing it, and there are many, many other ways being researched. Perhaps the simplest is just to flood the tumour with synthetic antibodies, ones that will recognize the tumour antigens and hopefully will therefore activate the immune cells despite the checkpoints. Probably the most powerful technique at the moment, and this was really the one for which the Nobel Prize was awarded, was the idea of checkpoint inhibition. So these are molecules, drugs that are injected that bind to those molecules on the tumour cells or to the counterparts on the immune cells and stop that checkpoint being activated. So they keep the immune cell on. Some of the first ones that were trialled were extraordinarily dangerous and led to some really horrible side effects, simply because these checkpoints are there for a reason. They've evolved because our body needs them. If we don't have them, that's autoimmune disease. So checkpoints are very, very important. We don't want to get rid of them. And say some of the initial checkpoint inhibitors sadly triggered some horrific immune responses and side effects that make chemotherapy, frankly, look tame. The more recent ones, however, are tumour-specific, and this is now a very, very exciting area. Many, many clinical trials ongoing with those. The parallel versions are to try to actually stimulate the production of the T cells themselves. So chemicals known as cytokines are injected to try to accelerate the production of immune cells that will go in and attack the tumour. And the last one, which you've probably seen in the news very recently, there have been some extremely exciting results from trials, are so-called cellular therapies. So this is where immune cells are extracted from individual patients, so immune cells that have already been tuned to a particular tumour. They are replicated outside the body, and then this army of T cells is re-injected, or in some cases they're actually genetically engineered to make them tumour-specific. And so these specialist T cells are re-injected into the patient to try to kill the tumour. Now, so far, success has been absolutely extraordinary in some patients and totally negligible in others, and it's only been effective in certain types of cancer. So it's been particularly useful in skin cancer and in leukemia. Solid tumours are still proving quite difficult to treat, but as I say, I gave a talk in 2017. I didn't even mention immunotherapy as a treatment. It's that recent that this has become a huge thing in cancer therapy, so there's very, very exciting changes to come. So that brings us on to where is all this going? I think it is worth sounding a note of caution. Just as in 1901, radiotherapy was being heralded as a potential cure for cancer, I think we have to be cautious in doing the same for immunotherapy. The results so far are incredible, but there are still a lot of problems. And earlier, I said that we are seeing a 20% reduction in cancer death rates. That's fantastic, but it's quite a moderate change given the amount of money that we're spending. This is the spend rate on cancer healthcare. It's growing every year, and it's growing at a faster rate than we're being able to improve efficacy. So there are lots of problems left to fix. Another thing it's very important to mention, I have been using the word tumour in a generic sense throughout the talk. That is slightly disingenuous. All tumours are very different types of cancer, different tumours of the same cancer in different patients, even different parts of tumours in different patients can respond very, very differently to treatment. And one result of that is we've seen very, very discrepant effects on different types of cancer. Prostate and breast cancer, progress has been absolutely remarkable over the last 30 years. Lung cancer and pancreatic, not so much. In fact, pancreatic cancer, survival rates haven't really improved since the 1960s. So there's a lot of work still to do. And there remain a lot of very fundamental questions. We still don't actually know what causes cancer. I said earlier something goes wrong with the DNA. We don't yet know what. There are many theories. This is hotly debated, but we don't know exactly what is causing the DNA to be damaged and leading to the development of tumours. We also have no idea why some people exposed to exactly the same risks develop cancer and some don't. We don't really understand cancer drug resistance yet, and as I've alluded to, we're still in the infancy of understanding cancer immunology and those interactions with the immune system. We have a lot of problems with developing better drugs. We need to work on how we can target those more effectively, and also why only some patients respond. If only it were just the science. There are huge economic questions to be answered. I've just shown the amount of money that's already being spent on cancer therapy, and the cost of drug development is growing every single year. It costs more than £10 million in 10 years now to develop a single drug. It takes a very, very long time, and this burden is falling on healthcare providers. Just to give you an example, a course of chemotherapy costs a few £1,000s. The cost of immunotherapy costs nearly £100,000 for a single patient. So that's putting it outside the ability of many people on the planet to ever receive these sorts of treatments. I think there are also quite a few ethical and political questions that need to be debated. As we develop these exciting new therapies, it's going to take a very long time for them actually to get into the clinic. Should we be letting terminal patients actually try them? This is a very interesting question. Different countries have different views on this. I mentioned genetic engineering, which is potentially an awesome power in treatment of many different types of diseases, but it throws up a whole host of ethical questions that need to be sorted out before we can turn this into a mainstream treatment. And should we leave this in the realm of pharmaceuticals, or should this be something we nationalise? Cancer vaccines are proving very effective. Is this something we should be rolling out across the world? And as we increasingly discover what causes cancer, or certainly we're able to correlate it to many of the things in modern life, should we actually be looking to ban some of those to reduce the risk of cancer? On a happier note, though, I want to finally explore one other area, which is really, really important and I think has a huge hope for future treatment of cancer, and that is trying to prevent it. So one of the reasons why we've been so effective in treating cancer over the last 30 years is not new drugs, it's actually earlier detection. Thanks to screening programs, we're able to catch particularly breast cancer and prostate cancer much, much earlier. And as you can see from this graph, that gives us a much better chance of effectively treating them. Screening programs are a lot cheaper than new drugs, and so this is probably something we should be looking at even more widely. Similarly, that increase in life expectancy that I talked about earlier in the talk was largely due to vaccination, to improved food security, to sanitation. It wasn't due to drugs. And so again, I think there are preventative measures we can potentially take that will help and keep the cost down. We've already seen that by banning asbestos, by trying to reduce air pollution, by banning smoking, that cases of lung cancer are starting to fall. And I think there are lots of other environmental risks that we can try to mitigate, stop cancer developing in the first place. And these are some new results, very, very exciting, on trials of human papillomavirus vaccines. So this is trying to prevent certain types of cancer in women. And as you can see, in a very, very short time, we've already seen a massive reduction in the rates of these types of cancer. Now, it's probably overly optimistic to think that we might be able to develop a universal cancer vaccine, but certainly for some types of cancer, this might be possible. And again, if we can prevent cancers from developing in the first place, then we don't have to worry about the cost of treating it. And finally, circling back to Hippocrates, there are many, many studies coming out now showing that there are even simpler measures that we can take to prevent cancer. Exercise, sunlight, sleep, fruit and vegetables, lots of fibre are being shown to have a really, really dramatic effect on the risk of cancer. Sadly, this does bring us to one more problem. This requires behavioural change, and as the last 2 years have brought into very stark focus, sometimes that can be easier said than done. So I think I would like to end with a plea for better communication of science. I think as scientists, we've got a huge responsibility to try to make sure that we are trusted and that the work we do filters through into the public, into medicine, and actually that's the way it's going to be effective. And that seems an appropriate note to thank Gresham College for facilitating a forum to do exactly that. Thank you once again. Thank you for listening. I'd be delighted to take any questions.
Has there been seen any link, negative or positive, between COVID and cancer?
Short answer, not to my knowledge. I think it's far too early to say. There are clearly going to be long-term effects on the respiratory system. Whether those have long-term effects, don't know, but yeah, there's no evidence that I'm aware of.
There's a couple of questions that ask about quite specific forms of therapy. I'm not sure if these, but I will ask them anyway, and we'll just see. How significant has gene therapy via CRISPR, C-R-I-S-P-R, been in curing cancer? Could it be viable to be used by the public in the near future?
Not in the near future, I think. So this is one of the big ethical issues. So CRISPR, if you're not aware, so this is an amazing technology. It's taken from bacteria. So it was discovered that certain types of bacteria are able to survive by altering the DNA of their attackers. They literally cut out chunks of DNA to stop their attackers from being able to replicate. And so this technology is now being applied for gene editing. Clearly got massive potential in cancer. It's being explored. I mean, I don't know how many papers are coming out on this, but it's daily, the number of papers coming out, but it's way, way too early for this to be a clinical study. And yeah, I think there are many years of clinical trials before we'll know.
Okay, and one more. Can you see CAR T cell therapy as a permanent form of cancer treatment in the future?
Excellent question. So CAR T-cell therapy is the one that was on the right-hand side of the screen in the immunotherapy slide. So this is where T-cells are deliberately engineered to attack an individual patient's cancer. So they're taken out of the body, they're genetically engineered and then re-injected. It seems to be very effective in certain types of tumour. These are the ones that are hideously, hideously expensive. And I think, unfortunately, that's going to be the rate-limiting step. It's not that it doesn't work, it really does seem to, but it's far too expensive at the moment. So unless someone comes up with a way to address the cost of it, we have a problem.
Eleanor, you said earlier that we shouldn't worry about 5G, but do you think there is any correlation between mobile phones and cancer, in your professional opinion?
There's no evidence. So I think I have to stand behind the scientific answer, which is we can only believe something when someone's done a study to demonstrate it. And a lot of people have looked. There's been no correlation found as yet. As always in science, there are never absolute definite answers, I'm afraid. But yeah, so far there's no evidence to that effect. I think there are plenty of other things wrong with mobile phones that we should limit use. But
So I've actually gone and going through a form of cancer. Touch wood, I've done better than expected. The one thing that everybody kept going on to me about was diet and sugar.
yes.
And they kept going on to the point that it really actually made me feel bad and guilty because I couldn't discipline myself in the food department because I'm an emotional eater, a sort of comfort eat, so that just made everything even more. So I was just wondering what your thoughts.
I think it's an area that needs a lot more work, but there are very, very clear relationships between diet and cancer, both the risk of it and response to treatment. Sugar does do a lot of damage. Unfortunately, I'm certainly addicted to it. It affects our microbiome, so this is something I didn't touch on because it's really not something we understand yet. But the bacteria in our guts is absolutely critical to the function of our immune system. And as a result is almost certainly linked to cancer. And we know that excess sugar is very, very bad for that. Clearly, risks such as diabetes, once you develop diabetes, that also impacts on your immune system. And so all of those together are why it is something that we...
It doesn't actually cause cancer.
I'd hesitate to give you a definitive answer on that. I mean, not directly in that you suck a lump of sugar and you'll definitely get cancer. Absolutely not. But I think there are many effects that excess sugar does produce that probably do increase our risk.
Thank you, that was really interesting. I've heard about the studies as well linking the microbiome with cancer and about how tumours have sort of very specific microbiomes around them. Why might that be?
Sorry, I missed the last bit.
Just about why tumours have such specific microbiomes around them and such different to like other parts of the body.
Excellent question. I don't think anybody knows. So just to elaborate on that, so even tumours have their own bacterial sort of makeup. It's amazing, and it is very, very different from in healthy tissue. Whether that's a cause, a consequence, has any impact, we don't know yet. I have very good colleagues in Oxford who are researching it very, very actively. We don't know. I mean, I think clearly trying to maintain a healthy microbiome is clearly extremely important. But yeah, I showed that complicated diagram. This is the problem. There are far, far too many things that are affected by everything, and we don't know yet.
Do you think that antibody carriers are as good for drug delivery as nanoparticles?
Ooh. Interesting. I mean, it's very difficult to compare them. So antibodies are used as a way of targeting drugs. So you attach the drug molecule to an antibody with the hope that it will then bind to the tumour cell. So it's a way of targeting the drug better. And as I explained about nanoparticles, the hope is that by making something of just the right size, that will end up in the tumour. I'm not aware of anyone having tried to do a like-for-like comparison. They both have the same problem, and that is because you have this incredibly chaotic structure of vessels in a tumour, anything you inject has a problem penetrating. So there are just regions of the tumour that are too far away to access the drug. And so, I mean, I'm starting to veer into my own research because this is the problem we try to tackle. But it is to try and improve that delivery, to find ways to overcome these barriers within the tumour to get enough drug in there. But yeah, so they've both got similar problems, but I'm not aware of a direct comparison, I'm afraid.
Okay, well, thank you very much. It was a wonderful lecture, really, really interesting. And I wanted to thank our audience for your attention and those of you online for engaging and participating. Let's all give Professor Stride a hand.